Right, so continuing from this, we have the states of matter. All right, so you have your three main states of matter: solid, liquid, and gases. So you have your solids arranged in a particular pattern, and then you have your liquids, which don't have a particular shapes, and they can shape to the container and the gas. Now, the main thing that you're gonna be asked here, okay, is to explain how a substance can go from a liquid to a gas to a solid in terms of energy, okay? So you want to say that the solids are arranged in a specific shape and pattern, okay? That will give you 1 mark. You say that they only have a little bit of energy, so they can only vibrate on a spot. That will be another possible mark. You will say that as you add energy to them, the particles will vibrate a lot stronger, and then they're gonna break the shape that they are, and they're gonna turn into liquids. That's gonna give you another possible mark. Now, when you look into liquid, the same thing applies. They don't have a specific shape. They have energy enough to slide over each other, and that's why they don't have a specific shape. If you carry on adding energy to it, those particles are gonna vibrate even harder, and then they eventually are gonna break the whole shape and turn into gases, where the particles or atoms are all going to be separated away from each other, because they got so much energy that they're bouncing off each other and colliding, and they are very far away from each other, okay? And that's what you want to talk about. Any of those three things. You want to talk about the shape that any of those three are. You want to talk about why they are in that shape. So in case of solids, they vibrate on a spot. They don't have enough energy to break the shape. Liquids, they have enough energy to slide past each other. And gases, they're very, very far apart from each other. And in terms of energy, solids got low energy, liquids got medium energy, and then you can say that gas have high energy, okay? So any of those probable 9 points will give you 5 marks, okay? If you're doing the higher, all you need to talk about, they might ask you, is to talk about the limitations of these diagrams, okay? That's what you want to look at. Why is it that this is not exactly accurate, or how those molecules change from liquid, gases, or solid, okay? You're gonna have to, let's see, predict the state of substances at different temperatures given appropriate data. Explain the different temperatures at which changes of states occur in terms of energy transfer and types of bonding. So this is what we're talking about over here. Recognize the atoms themselves do not have a bulk properties of materials. Alright, and explain how the limitation of particle theory relates to the changes in states. Right, so this one here specifically is because it's telling us that the atoms, so for instance, you have sodium chloride, right? Sodium is an explosive metal when you put it in contact with water, and salt is a poisonous gas. Chlorine is a poisonous gas, but when you join them together and you make salt, it's not either explosive or poisonous, okay? So that's one of the things you want to remember, that the atoms will have, the elements will have specific properties, but once they form bonds and make covalent bonding or ionic bonding or even metallic bonding, their properties might slightly change. In case of the metals and metallic bonding, it will change if they are turned into alloys, and we'll have a look at that in a few minutes. Okay, then we have state symbols. We all know what state symbols are: S, L, and G for solid, liquid, and gas, and you have AQ, which is aqueous, okay? An aqueous solution is essentially a solid that has dissolved in a liquid, okay? In this case, you can also say a solute would be the solid, and then has dissolved in a solvent, which should be the liquid, okay? So in the instance, I don't know, we have sugar and water, and then you have salt and water. You can make aqueous solution. You can make a sugary aqueous solution, or you can make a salty aqueous solution, okay? We're looking at properties of ionic compounds. Ionic compounds have regular structure. This is what we talk about, the giant lattices. It takes a lot of energy in order for them to be melted, because of the giant lattices, or the attraction between the molecules makes them very, very strong, okay? And so another way to do that is that most of salts, you can dissolve them in water, you can dissolve them in any other type of solvent, and then you'll be able to separate them without having to actually use too much energy. So knowledge about the structure-specific ionic compounds other than sodium chloride is not required. So all you want to familiarize yourself mainly is with sodium chloride, okay? Because you need a lot of energy to actually melt. I think it's 609 degrees. Whilst if you just dissolve it in water, it's just going to be a lot easier, okay? And when we're looking at properties of small molecules, substances that consist of very small molecules, gases, liquids, are relatively low melting points and boiling points. These substances have only weak forces between the molecules, the weak intermolecular forces. So this is what we said before, that if a covalent molecule has only a couple of atoms, is going to be a simple covalent structure, and they are very easily changed because they have very low melting and boiling points. They can change states very easily. You don't need a lot of energy to do though, okay? And that's because they have very weak intermolecular forces. The intermolecular forces are very weak, and the actual ionic bonds and covalent bonds and metallic bonds, those are strong, okay? But the intermolecular forces are weak. So if you look at over here at the top, and we look at this molecule here, loads of those molecules are going to be very close to each other, but because this here is a covalent bond, covalent bond, covalent bond, that's strong, okay? But when there is another molecule similar to that just next to each other, they're not going to be very attracted to each other, or they will be very easy broken apart from each other because the bond between the intermolecular force between this molecule and the other one is very weak, okay? Okay, so we go back to over here. That's what we said over here. And then we have polymers. Polymers, very large molecules. They can be made with a couple hundreds, thousands, even millions of molecules, right? And they have very strong covalent bonds. We look at giant covalent structures, and in those you can look at something like sand, which is silicon dioxide. You'll be looking at diamonds, graphite, graphene, nanotubes. All of those are examples of giant covalent structures because all of those will have millions of atoms joining together with actually covalent bonds, not intermolecular forces, which are weak. When looking at properties of metal alloys, metals have giant structure, and atoms are very strong metallic bonding, right? They have very high melting point, high boiling points. They are sonorous, so that means the sound can go through them. They're malleable, you can change it into different shapes. They're ductile, you can turn them into wires and stuff like that. Some of them will be, well, not the alloys, but some of the metals will be magnetic, okay? But when you join different metals with other stuff in it, you make alloys, and those alloys normally are stronger than the metals, the normal metals, because the structure changes, okay? The structure changes, and therefore they are not in a very straight pattern anymore. They are in a very irregular pattern. It takes a lot more energy to bend them, and therefore that's why alloys tend to be a lot stronger. So one of the examples, you have the steel. Steel is an alloy of iron. It just basically has carbon in it, and that makes it a lot stronger than the normal iron, okay? Metals, as conductors, you know, they can use conduct electricity and heat. Electricity mainly because of the delocalized electrons. You might be asked why diamonds are so strong, and you will say because in diamonds every carbon joins to another 4 carbons by covalent bonds, which are very strong bonds, okay? And that's why diamonds are hard. And then in graphite, why does it conduct electricity? Because they have sparse electrons in the outermost shell, and once they join into 3 other carbons, you have 1 electron which is free to transfer the electricity, okay? You're looking at graphene and fullerenes. Those are some of the carbon allotropes. They might ask you to identify which one of these figures are carbon allotropes and what is a carbon allotrope, which is basically a structure of an element that's got different amount of the element has been combined in different ways, so they have different types of shapes, forms, and quantity of atoms, okay? And then we're looking at bulk surfaces of metals, including nanoparticles. This is only if you're doing a triple, where you have to try to calculate the sizes of nanoparticles. You'll be looking at nanoparticles, which are what are the uses, and we were looking at trying to get examples of nanoparticles in terms of what the uses are. You have silver nanoparticles that can be used for medicine. You can use them for killing bacteria in clothing. You can use silver nanoparticles for the use of sunscreen. So you gotta familiarize yourself with what nanoparticles are and what are the uses of nanoparticles, okay? Okay, so that's all we got for that specific part of the paper 1. If you find that useful, like and subscribe, and if you have any questions, you can write down your questions in the comment section, and I'll try to get back to you as soon as possible. So see you next time.